Good evening everyone, good evening. I welcome you all again to NEET Elite. I hope you guys are doing great, having a good time. So people, you can first of all let me know in the chats if I'm audible and visible to everyone. Just let me know in the chats. Give me some green signal from the chat box so that I'll get to know that I'm audible and visible to you. Hello Tanzila, hi Inabat, hello Akshay, hi Ashwarya, hi Ishpreet, hello Amulya. Hello Bibek, hi Akash, welcome back everyone, welcome back. Just let me know in the chats if I'm audible and visible to everyone. Yes, give me some green signal from the chats. Alright. Perfect guys, perfect. Hello Shrijan, hi Ashika, hi Shriharan, welcome back everyone. Hello Sahil, walaikum salam. Hello Maisha, hi Sweetie, hello Shawad. Perfect guys, so as you all must be knowing, tonight it's going to be our 6th session, I guess, from the chapter chemical bonding, right? And if you remember in the last session, we finished till hybridization is done, right? Everything is done till hybridization, VSC, PR, VBT, right? We have discussed every single thing. And in the tonight's session, we are going to discuss one of the most important theories of this chapter. That's something which I call as molecular orbital theory. One of the most important theories from this chapter, from which question frequently comes in your NEET examination, right? Perfect. So people, before starting the session, the ones who are new to the channel, let me introduce myself. Well, my name is Wassim Sir and I'm your chemistry master teacher writer on this NEET Elite channel, yeah? The ones who have not liked the video yet, please do like the video, share the video with friends, do subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which I take live on this NEET Elite channel, yeah? So do like the video, share the video with your friends and do subscribe to the channel as well, okay? Yes. So people, you can let me know in the chats if you guys are super duper excited about this session as well, yeah? Let me know in the chats if you people are super duper excited about this session as well. Well, I might sound a little low tonight because I'm not well. I'm having some cough, cold, yeah, everything. So I hope that's fine, yeah? That's great, Ashwarya. Josh must be always high, yeah? So welcome back everyone, welcome back. After so long we are meeting, yeah? Perfect. So let's get going then. Let's get started with one of the most important theories of this chapter, which is what we call as molecular orbital theory, yeah? Okay. So people, let's get to know some important postulates of this theory so that you can understand it properly, okay? First, I'll be giving you the postulates. Then after like 5-10 minutes, I'll be making you understand all these postulates in detail, right? It might look tough in the starting, but eventually it's going to be fine for you, okay? So be positive. Perfect. The first point about this molecular orbital theory, it is the extension of the valence bond theory. It is the extension of VBT. Right? What that means exactly? What is meant by the statement, it is the extension of VBT. See guys, exactly. As you all must be familiar with the fact, in VBT, I mean VBT used to explain us how covalent bonds get formed, how your sigma and pi bonds get formed in the molecules, right? That was explained by VBT, if you remember, correct? By means of axial overlapping, parallel overlapping, everything we have discussed in detail, right? So how come basically this is the extension of VBT? Let me give you the idea about that. See guys, if you talk about the valence bond theory, right? Let's say, as per valence bond theory is concerned, atomic orbital of one bonding atom and the atomic orbital of one more bonding atom, they used to do the overlap, right? And after the overlap, they used to lead to the formation of either sigma bonds or they used to lead to the formation of pi bonds. Well, sigma bonds used to get formed by the axial overlap of the atomic orbitals of the bonding atoms, and pi bonds used to get formed by the lateral overlap, by the sideways overlap of atomic orbitals. I hope you remember that, right? Your axial overlap, it leads to the formation of sigma bonds as per your valence bond theory is concerned, and your sideways overlap, it leads to the formation of pi bonds as per your valence bond theory is concerned, right? Now have a look exactly what we have discussed in VBT and how come it's going to be, this MOT is going to be the extension of VBT. Have a look exactly guys. See, let's say this is one of the atomic orbital, let's say this is some 1s atomic orbital of some atom A, right? Let's assume this is again 1s atomic orbital of some other atom A, right? So these two atoms, these two atomic orbitals, 1s of A and 1s of A, right? As we have discussed, they are going to overlap axially, and when there will be axial overlap, they will lead to the formation of molecular orbital. They lead to the formation of molecular orbital. And that molecular orbital, if you remember, that used to be like this. That used to be like this. Correct? This used to be one of the nucleus of the atom, one more nucleus of the atom, and in the middle we used to have the electron density, right? This electron density used to arrange itself in such a way that it comes under the influence of both the nuclei. And this orbital which we used to get, right? When these atomic orbitals used to overlap with each other, this orbital we used to call as molecular orbital. And since this is the head-on overlap, this is the axial overlap, the bond which used to get formed in this case used to be the sigma bond. I hope you remember that, right? Similarly, let's say I've got one of the p orbital of one atom and one more p orbital of another atom, right? Okay. They used to do which kind of overlap? See, this is the axis of this atomic orbital which I'm talking about. This is the axis of this atomic orbital. Since their axes are parallel to each other, so they are going to show the parallel overlap, and after the parallel overlap, right, the parallel overlap, sideways overlap, it leads to the formation of pi bond. So basically what happens over here, when these atomic orbitals, when they'll try to overlap with their axes parallel, what is going to happen? We used to get one molecular orbital like this. We used to get one molecular orbital like this. I hope you remember it. Correct? This used to be one of the nucleus of this atom, and this used to be one of the nucleus of this atom. I hope you remember this. Correct? This is one molecular orbital which we got over here. And which kind of bond we got in this case? This used to be the pi bond. This used to be the pi bond, right? As per your valence bond theory is concerned, when two atomic orbitals combine, they will lead to the formation of one molecular orbital. Similarly, when these two atomic orbitals will combine, they will lead to the formation of one molecular orbital, right? But as per molecular orbital theory is concerned, the number of atomic orbitals combining is always equal to the number of molecular orbitals formed, right? As per VBT, when two atomic orbitals used to combine, they lead to the formation of one molecular orbital, right? Like this. Similarly, two atomic orbitals are combining, they will lead to the formation of one molecular orbital as per VBT. But as per molecular orbital theory, the number of atomic orbitals combining is always equal to the number of molecular orbitals formed, right? Let me write it over here. For example, this is one of the atomic orbitals of one atom, and it's going to combine with one more atomic orbital of one more atom. Since two atomic orbitals are combining, as per your molecular orbital theory, they will lead to the formation of two molecular orbitals. They lead to the formation of two molecular orbitals, right? Two atomic orbitals of two bonding atoms, right? They are going to combine. They will lead to the formation of two molecular orbitals. One of the molecular orbital is something which we call as bonding molecular orbital. Another one is called as anti-bonding molecular orbital, right? Do remember these things first of all. I'll show you exactly how these bonding and anti-bonding molecular orbitals are going to get formed. That's something which I'll be showing you in some time. But remember first of all these things, yeah? Do remember one more thing. This bonding molecular orbital which gets formed, remember, energy of bonding molecular orbital is always lesser than that of energy of anti-bonding molecular orbital, right? If energy of bonding molecular orbital is less, that means the stability of bonding molecular orbital is going to be more than that of the stability of anti-bonding molecular orbital, right? Low energy means more stability. So when two atomic orbitals will combine, they will lead to the formation of two molecular orbitals. One is something which is called as bonding molecular orbital. Another one is anti-bonding molecular orbital. Do remember right now, energy of bonding molecular orbital is considered to be less than that of energy of anti-bonding molecular orbital, right? So eventually, the stability of bonding molecular orbital is absolutely going to be more than that of stability of the anti-bonding molecular orbital, right? I'm sure it's clear till here. I'll show you exactly how this all happens, okay? But remember this thing first of all, correct? Now guys have a look. This is something which I told you, atomic orbitals as per MOT is concerned, as per molecular orbital theory is concerned. Atomic orbitals combine to form molecular orbitals as per what? As per your molecular orbital theory is concerned. And the number of atomic orbitals formed is always, the number of molecular orbitals formed is always equal to the number of atomic orbitals combined, right? Let's take certain examples so that it gets clear to you. See, this is something which I told you. One of the atomic orbital of one atom and one of the atomic orbital of one more atom, they are going to combine. They are going to lead to the formation of two molecular orbitals. One is called as bonding molecular orbital, one is called as anti-bonding molecular orbital, right? Okay, for example, let me take this scenario like this. Have a look exactly what I'm going to talk about. See guys, this is first of all one s atomic orbital of some atom A, right? This is again one s atomic orbital of some atom A, right? These two A atoms, they are going to form the bond. They are going to form the bond, right? As per your molecular orbital theory is concerned, in order to form the bond, these two atoms, these two atomic orbitals, they must approach each other first of all so that they combine. So first of all, combination of these atomic orbitals is going to take place, right? Since two atomic orbitals are combining, so how many molecular orbitals are going to get formed? Two molecular orbitals are going to get formed. One will be bonding, one will be anti-bonding, right? Since this is the s orbital, even this is the s orbital, and we have seen s orbitals, they always do the axial overlapping. They always do the axial overlapping. That's something which we have discussed. And axial overlapping always leads to the formation of sigma bond, right? Okay. So over here, since two atomic orbitals are combining, so two molecular orbitals will be getting formed, right? One is going to be bonding molecular orbital, one is going to be anti-bonding molecular orbital, right? This bonding molecular orbital, since these are doing the axial overlapping, so bonding molecular orbital I'll be representing by sigma 1s, and this anti-bonding molecular orbital which is getting formed, I'll be representing with sigma star 1s, right? Star means anti-bonding, right? And we have discussed energy of bonding molecular orbital is slightly lesser than that of energy of anti-bonding molecular orbital, due to which stability of bonding molecular orbital will be always more than that of stability of anti-bonding molecular orbital, right? Do remember this thing as well. Yes? I'll be showing this in detail. I'm just giving you the quick overview of the postulates first of all. I'm not teaching right now in detail, right? After some time, I'll be teaching all these things in detail. But this is the quick overview of all these things first, all these postulates. Correct? So one is called as sigma 1s, one is called as sigma star 1s. Yeah? Now, this is something which I've discussed. Energy of anti-bonding molecular orbital is always greater than the energy of bonding molecular orbital, right? For example, sigma 1s which got formed due to the, which is basically the bonding molecular orbital, right? Its energy is less than that of sigma star 1s, which is basically the anti-bonding molecular orbital, correct? One more thing guys. As per your molecular orbital theory is concerned, see, first of all, these atomic orbitals, they combine. They lead to the formation of molecular orbitals, right? Once these molecular orbitals are formed, after that, we are going to arrange the electrons in these molecular orbitals, right? The way we used to write the electronic configuration in atomic structure, in the same way, once the atomic orbitals of the bonding atoms combine, once they lead to the formation of the molecular orbitals, once you'll be having molecular orbitals with you, then you are going to fill electrons in those molecular orbitals, as per, again, a Bose principle, as per Hund's rule, as per Pauli's exclusion principle, right? And once electrons are filled in those molecular orbitals, correct? Then do remember one thing. As the number of electrons in bonding molecular orbital increases, stability increases, and if the number of electrons in anti-bonding molecular orbital increases, the stability decreases, right? So in short, more the number of electrons in bonding molecular orbitals, more is going to be the stability of the molecule. Similarly, more the number of electrons in anti-bonding molecular orbitals, lesser is going to be the stability of the molecule. Do remember this thing as well, okay? More the number of electrons in bonding molecular orbitals, more is going to be the stability of the molecule, and more the electrons in anti-bonding molecular orbitals, lesser is going to be the stability of the molecule. Do remember this thing as well, this one more postulates, right? And I told you, while filling the electrons in molecular orbitals, you need to take three principles into consideration. One is a Bose principle, Hund's rule, as Pauli's exclusion principle, right? Once atomic orbitals combine, once they lead to the formation of molecular orbitals, after that you are going to fill the electrons in those molecular orbitals as per a Bose principle, Hund's rule, and Pauli's exclusion principle. Do remember this statement as well, okay? This molecular orbital theory, it's going to give you the idea about the bond order of the molecule as well. Now, first of all, what is bond order? Bond order is nothing. It is just the number of bonds between two atoms in a molecule. The number of bonds between two atoms in a molecule. For example, there is a single bond between two atoms. There is a single bond between two atoms A, right? Similarly, let's say there's a double bond between these two atoms. Let's say there's a triple bond between these two atoms. I'll clearly say bond order of this molecule is 1 because there is only one bond present in between them. So bond order of this molecule is going to be 2 and bond order of this molecule is going to be 3. So bond order simply gives you the idea about the number of bonds between two atoms in the molecule, right? And this molecular orbital theory, by means of this formula which I mentioned over here, by means of this formula, you'll be exactly calculating the bond order of any molecule, right? Okay. Now what is this formula all about? Bond order, which is basically the number of bonds between two atoms in a molecule. Yes, it is always equal to half of Nb minus Na. What is Nb? Nb, it simply is number of electrons in bonding molecular orbital. And Na, this is something which we call as number of electrons in anti-bonding molecular orbital, right? Anti-bonding molecular orbital, correct? This is something which I'll be teaching you in detail in some time, right? These are the main postulates, right? These are the main consequences of this molecular orbital theory. Few more interesting things. Remember, by using this formula, if bond order of any molecule comes out to be less or equal to 0, remember that molecule won't be existing. That molecule does not exist. If for any molecule, the bond order by using this formula comes out to be less or equal to 0, remember that molecule does not exist. If the bond order comes out to be 1, that means there's a single bond existing between two atoms in a molecule, right? If the bond order comes out to be 2, remember, there are 2 bonds between the two atoms in the molecule. Similarly, if the bond order is 3, there's a triple bond between two atoms in a molecule. Do remember these things as well, yeah? Now, remember one more thing. Bond order is related to bond strength as well as bond length. Bond order is related to bond strength as well as bond length. For example, if I say more is the bond order, what does that mean? If I say more is the bond order, what does that mean? That means more are the bonds present between the atoms in the molecule. More are the bonds present. What is a bond basically? Bond is a force of attraction. More the bond order, that means more will be the bonds present. More the bonds means more will be the force of attraction between the two atoms. And if more is the force of attraction between two atoms, less is going to be the bond length, right? Yes, and more is going to be the bond strength. More is the energy needed to break that bond. Yes, so remember, more the bond order means more are the number of bonds. More bonds means more force of attraction. More force of attraction means less bond length. Less bond length means more is the bond strength. More is the energy needed to break that bond. I'm sure this statement is also clear to you. Do remember this as well. Okay? Right? Similarly, for example, if I'll be having a single bond between two atoms, then I've got double bond between two atoms, then I'll be having triple bond between two atoms. You can easily talk about the bond strength of these bonds. You can talk about the bond lengths as well. See, which of the following, wherein you are seeing the maximum bond order? Maximum bond order is in this case 3. Maximum bond order means maximum bonds. Maximum bonds means more force of attraction between the atoms. More force of attraction means less the bond length. Less bond length means more will be the strength of the bond. As simple as that, right? Okay, so if I talk about the bond length is going to be the minimum in the last case because there is a triple bond. There is more force of attraction between the atoms. Atoms would have come a little more closer compared to this as compared to this, right? Do remember these things as well. Correct? These are some basic things which you must remember. Now, as for your molecular orbital theory is concerned, atomic orbitals of two bonding atoms, they are going to combine, they are going to lead to the formation of molecular orbitals, right? Now, what are the conditions for the combination of these atomic orbitals? What conditions the atomic orbitals must follow such that they can combine, they can lead to the formation of molecular orbitals, right? Let's talk about those conditions first of all. Conditions for what? Conditions for combination of atomic orbitals. The first condition, atomic orbitals must be having almost similar energy. What does that mean? What does that mean? Let's say I'll be having one s atomic orbital of one atom A, one s atomic orbital of some other atom A, for example, right? Let's say these are two bonding atoms A and A. They are going to form the bond. See, this atomic orbital 1s, this atomic orbital 1s, right? They have got same energies. So they can combine, they will lead to the formation of molecular orbitals. One is going to be bonding, one is going to be anti-bonding, right? If it is going to be, for example, like this as well, 2s and 2p, 2s of one atom and 2p of one atom, even they can combine, they can lead to the formation of molecular orbitals because their energies are comparable, right? They have got almost similar energies, 2s and 2p. But 1s and 5p, for example, they cannot overlap. I mean, they cannot combine, they cannot lead to the formation of molecular orbitals because the energy gap is too much, right? The energy difference is too much, right? So those two atomic orbitals of bonding atoms are going to overlap, are going to combine, right? Which have got either same energy or comparable energy, right? Those atomic orbitals of two bonding atoms which have got larger differences in the energies, those are not going to combine, those are not going to lead to the formation of molecular orbitals, right? So I would have mentioned it over here as well. 2s, 2s, it can show the combination. It can lead to the formation of molecular orbitals. Even 2s and 2p, they can lead to the formation of molecular orbitals, but this 2s and 5p, no way, they are not going to form any molecular orbitals, right? Do remember this thing as well. Now, this is one important point. Both the atomic orbitals must be symmetrical along the axis. What does that mean? What does that mean? Have a look. Have a look, guys. Let's say this is one of the atomic orbital of one atom, and this is one more atomic orbital of one more atom, right? Let's assume this is 2px of one atom, this is 2px of one more atom, right? First of all, this is the axis of it, this is the axis of it, right? I'm considering the x-axis as the internuclear axis. Now, first of all, if this is 2p, this is 2p. Are they going to combine? Right, they are going to combine. They lead to the formation of molecular orbitals, right? So first of all, what kind of combination they'll show? What kind of overlap they'll show? They'll show the sigma overlap, right? I mean, they'll show the axial overlap. And axial overlap always leads to the formation of sigma bonds, right? So over here, I'll be getting two molecular orbitals. One is going to be bonding, one is going to be anti-bonding. Which one? Bonding, I'll be representing with sigma 2p x, and anti-bonding, I'll be representing with sigma star 2p x. Right? As simple as that. So this kind of combination is possible. This kind of combination is possible. Similarly, if this is, for example, 2py, this is 2py. Let's assume this is 2py, this is 2py atomic orbital of two bonding atoms, right? Now, they can also combine. This is 2py, for example, this is 2py. Correct? Even they can combine. They can combine. They will lead to the formation of the molecular orbitals. And what kind of overlap they are going to show? They are going to show the parallel overlap. They are going to show the sideways overlap, right? And they will again lead to the formation of two molecular orbitals. One bonding, one anti-bonding. But the overlap is parallel, and parallel overlap leads to the formation of what? Pi bonds. So one is going to be over here as pi 2py molecular orbital. One is going to be pi star 2py. This is what I'll be calling as bonding molecular orbital. This is what I'll be calling as anti-bonding molecular orbital. As simple as that, right? But if the case is like this, let me show it to you. If the case is like this, let's say this is one of the atomic orbital of one atom, and this is one of the atomic orbital of one atom. Their axes are perpendicular. Their axes are perpendicular, right? So can they show any sort of overlap over here? They are not going to show any sort of overlap, right? So orientation of atomic orbitals must, right? Okay. These two are not going to show any sort of overlap. Either it should be head-on overlap or it should be parallel overlap, right? Axis, the atomic orbitals having axes perpendicular to each other, they are not going to combine at all. This is not the proper orientation of the atomic orbitals to combine, to form the molecular orbitals, right? Yes, so both the atomic orbitals, they must be symmetrical along the axis. And this is the case which I've shown already. This is the axial overlap which is going to be, this is the parallel overlap, and over here no overlap is going to happen. Yeah, as simple as that, correct? Okay, now let's exactly move on. Let's exactly see how these molecular orbitals will be getting formed. Now actually I'm going to start the molecular orbital theory. Till now this was all basics. I'm sure you'd have got all the concepts, all the points till now. Yes? Okay, now exactly I'm going to teach you the molecular orbital theory in detail, right? How these molecular orbitals actually get formed, right? Why the energy of bonding molecular orbital is less, why the energy of anti-bonding molecular orbital is more. That's something which I'm going to discuss in detail now, right? You can let me know in the chats if every single thing is clear till here so that I can move on. Let me know fast, people in the chats, if everything is clear till here so that I can move on fast. Yeah? Perfect, guys. So let's move on. Formation of molecular orbitals. How these molecular orbitals are going to get formed. It is going to be explained by LCAO, linear combination of atomic orbitals. Linear LCAO, this is something which is going to explain the formation of molecular orbitals, right? What it means exactly. What it means exactly. See guys, exactly what it means. For example, I'm taking the atomic orbital of one atom A, one bonding atom A, and this is one more atomic orbital of one more atom, right? These are the two atomic orbitals of two bonding atoms which are going to form the bond first of all, right? First of all, in order to form the bonds, as for the molecular orbital theory is concerned, what they have to do? They need to show the combination, right? These two atomic orbitals, they should combine. After the combination, they should lead to the formation of molecular orbitals, right? And how these molecular orbitals are going to get formed. See guys, we have discussed in atomic structure, your atomic orbital predominantly has got the wave nature. Your atomic orbital predominantly it has got the wave nature, right? So this atomic orbital, it's basically a wave, and I can show it to you like this. This is basically a wave like this, right? Let me show you the signs as well, positive, negative. This positive, negative, it has got the significance as well. Let me tell you that in some time. Similarly, this is one more atomic orbital of some other atom, right? This is the wave associated with this atomic orbital over here, right? This is the wave corresponding to this atomic orbital, right? Let me give this the positive sign, give this the negative sign, right? This can be basically when atomic orbitals, how these atomic orbitals combine and lead to the formation of molecular orbitals. This is explained by the linear combination of atomic orbitals, right? And we know atomic orbitals, they have got predominantly wave nature, right? So this atomic orbital, right? This is the wave of this atomic orbital, right? This atomic orbital, you can show, this is the wave which is basically corresponding to this atomic orbital, right? So this can be one of the scenarios in which these two waves are going to show the interference, right? These two waves are going to show the interference. These are basically the atomic orbitals, right? Okay, these are atomic orbitals, or you can call them as the waves as well. These are going to show the interference. These are going to show the interference. And how they are going to show the interference? See, this is one of the way by means of which they can show the interference, or let me show it to you like this as well. This can be one of the way. This is positive, negative, and this atomic orbital's wave, I can represent it like this. This is negative, this is positive. Correct? Right? In the first scenario, these two waves, they are in phase. They are in phase. They are in phase. See guys, positive, both the waves are starting from here, right? Both the waves are moving together like this, right? But over here, both the waves, these are not in phase. These are out of phase. These two are out of phase. These two are in phase. These two are out of phase. These two waves, these are going to start simultaneously like this. These are going to move simultaneously like this, right? Okay. These two are out of phase. And when two waves are in phase, they always show the constructive interference. They always show the constructive interference. And when the two waves are out of phase, they always show the destructive interference. Remember, constructive interference always leads to the formation of the molecular orbital, right? It leads to the formation of molecular orbital. These are basically two atomic orbitals which are combining, right? Okay, these are the two waves which are combining. And which kind of interference this is? This is constructive interference. And in case of constructive interference, the amplitude of the resulting wave will be maximum like this. This is the amplitude of the resulting wave which is maximum, right? But in case of destructive interference, see guys, this is positive, this is negative, right? They are out of phase, right? They are going to show the destructive interference. So the resulting wave which gets generated over here, that its amplitude is going to be minimum like this. This is the amplitude of the resulting wave, minimum, correct? So remember, the constructive interference, it's going to lead to the formation of the resulting wave whose amplitude is going to be maximum, right? And over here, you are getting the resulting wave whose amplitude is going to be the minimum, right? Now let's talk about this constructive interference and destructive interference in detail, right? But before that, let me tell you, whenever two waves are going to show, whenever two waves corresponding to two atomic orbitals, whenever they show the constructive interference, it always leads to the formation of bonding molecular orbital, and this leads to the formation of anti-bonding molecular orbital. Basically, this wave, this resulting wave over here, right, it corresponds to bonding molecular orbital, and this resulting wave, it corresponds to the anti-bonding molecular orbital. Yeah? Now let's talk about the constructive and destructive interference one by one in detail. Yeah? Let's have a look guys, what I'm going to talk about now. When two waves combine in same phase, the resulting amplitude of the wave increases. What that means. Have a look now what I'm going to talk about, correct? As I told you, constructive interference, it leads to the formation of bonding molecular orbitals, and destructive interference, it leads to the formation of anti-bonding molecular orbitals. Have a look. Currently, I'm going to show the constructive interference. Yeah? See guys, this is atomic orbital of some bonding atom, right? And this is one more atomic orbital of some other bonding atom, right? Currently, I'm going to show you the constructive interference, and due to constructive interference, the molecular orbital which we get, that's what we call as bonding molecular orbital, right? And let's exactly see how it gets formed. See, For example, this is the atomic orbital, right, which I can represent through a wave as well. This is a wave. This is one more atomic orbital which I can represent through a wave as well. This is a wave. This is positive, for example. This is negative. This is positive. This is negative, right? Whenever there is constructive interference. First of all, are these two waves in phase or out of phase? These two waves are in phase. And when the two waves are in phase, whenever they show the interference, which kind of interference they are going to show? They are going to show the constructive interference, in which the resulting wave is going to be like this. In which the resulting wave is going to be like this. This is the wave corresponding to bonding molecular orbital. This is the wave corresponding to this atomic orbital. And this is the wave which corresponds to this atomic orbital, right? Okay. See, let's say guys, this is atomic orbital of some atom A, this atomic orbital of some atom B, right? Atom A and B, basically they are going to form the bonds, right? So this is the atomic orbital of atom A, this is the atomic orbital of atom B. Now understand what I'm going to talk about. See guys. First of all, let me tell you, amplitude of this wave is represented by psi A. Amplitude of this wave is represented by psi B. And what about the amplitude of this wave? This is the constructive interference, right? Amplitude of this wave is going to be psi A plus psi B. This is the amplitude of the wave, right? Okay. Now people, if I do square of this psi A, if I do square of this psi A, if I do square of this psi B, what it means exactly? Square of A, square of psi A, what does that mean? It gives me the probability of finding the electrons around the nucleus in atom A. This gives me the probability of finding the electrons around the nucleus in atom B, right? So square of amplitude basically gives us the electron density around the nucleus, right? Square of psi square, it gives us the electron density around the nucleus, right? In the atoms. Square of amplitude. Yes, that's something which we have discussed in atomic structure as well, correct? Now people, psi square is giving you the probability of finding the electrons around the nucleus in atomic orbital A, right? Psi square B, probability of finding the electrons around the nucleus in this bonding atom B, right? Now, constructive interference has happened. The resulting wave, it corresponds to bonding molecular orbital, right? Its amplitude is psi A plus psi B. If I do the square of this amplitude, what do I get? I get psi A square plus psi B square plus 2 times psi A psi B. This is something which I got till now, correct? This is something which I got, correct? This term is giving me the probability of finding the electron around the nucleus in atom A, probability of finding the electron around the nucleus in atom B, probability of finding the electron in between the nuclei in the molecule, right? See, this is basically atomic orbital, this atomic orbital, this is the molecular orbital actually, right? This is the molecular orbital, correct? This is the molecule which has got formed basically. It's a molecular orbital, correct? So psi square is giving me electron density, probability of finding the electron density around A, probability of finding the electron density around nucleus of B, right? This term, this psi square plus psi B square plus 2 times psi A psi B, this is basically giving me the probability of finding the electron between the nuclei of the two bonding atoms which have formed a molecule, right? Now, as per your common sense, understand. Psi square is giving us the probability of finding the electron around the nucleus in atom A. This is giving us the probability of finding the electron around the nucleus in atom B. Now these two atomic orbitals are combining. So I was expecting the probability of finding the electron in this molecular orbital should be psi A square plus psi B square. Just the addition of these two, right? That's something which I was expecting. But the probability of finding the electron over here is psi A square plus psi B square plus 2 times psi A psi B. So is the probability of finding the electron between the nuclei of the two bonding atoms increased in this molecular orbital or not? I'll say yes, the probability of finding the electron between the nuclei of the two bonding atoms in this bonding molecular orbital, it has got increased by this much of amount. It has increased by this much of amount, right? And if the electron density between the nuclei in the molecular orbital is increasing, I'll say repulsions between the nuclei will decrease. And if repulsions between the nuclei will decrease, what is going to happen? Energy of the molecular orbital will decrease, right? And the stability of the molecular orbital will increase, right? This kind of molecular orbital, which we get over here, that's what we call as bonding molecular orbital, whose energy is less, whose stability is more. I hope you got it. So normally what I was expecting? I was expecting the electron density between the nuclei of the bonding atoms A and B should be psi A square plus psi B square, but actually it's coming out to be psi A square plus psi B square plus 2 times something. So this term is being added over here, right? So the electron density between the nuclei has increased a bit by this much of amount, right? So electron density has increased between the nuclei in the molecular orbital. If the electron density has increased, that means the repulsion between the nuclei will decrease. If repulsion between the nuclei is decreasing, that means energy of the molecular orbital will decrease and stability will increase. And due to this constructive interference, which kind of molecular orbital gets formed? Bonding molecular orbital whose energy is less, stability is more. That's something which I told you in the beginning also. I hope you remember. Correct? Now let's talk about one by one by means of constructive interference how come these molecular orbitals are getting formed, right? This is something which I've shown you over here. Correct? So electron density in this bonding molecular orbital is increasing by this much of amount, 2 times psi A psi B. That's it. Yes? Correct? So when two waves combine in same phase, right, electron density around the nuclei increases, right? And bonding molecular orbital is formed. That's something which I told you, right? Let me show you exactly how this bonding molecular orbital exactly looks like. Have a look, guys. Have a look first of all. This is, for example, 1s atomic orbital of atom A. This is 1s atomic orbital of atom B, for example, right? Okay. I've given these signs minus, plus, plus, minus, right? Just to make you understand one thing. Remember, when two same signs will be on same side, that means constructive interference is going to happen. And due to constructive interference, which molecular orbital gets formed? Bonding molecular orbital gets formed. And in the bonding molecular orbital which gets formed, the electron density between the nucleus will be more, due to which repulsion between the nuclei will be less, stability will be more, right? So how this bonding molecular orbital gets formed due to constructive interference? Have a look. It's going to be like this. Say guys, this is the negative, this is minus. So let's keep this minus, and in the middle, the electron density has increased over here like this. Okay, I'm giving this a plus sign over here, right? So first of all, due to constructive interference, which kind of molecular orbital gets formed? Bonding molecular orbital. So this is basically the bonding molecular orbital, right? Now, if this is the bonding molecular orbital, understand one more thing. Was here axial overlap or sideways overlap? It was the axial overlap. Axial overlap always leads to the formation of sigma bond. So this will be sigma. I'll be calling this as sigma 1s molecular orbital. Which got formed due to the constructive interference, right? This was case number 1. When 1s of one atom, when they combine, right? When they show the constructive interference, they lead to the formation of bonding molecular orbital, which I represent by sigma 1s, right? I'm sure it's clear to everyone. Yeah? Now guys, if I talk about the nodal plane in this bonding molecular orbital, people, there is no plane which exists over here as such. Which cuts this molecular orbital in such a way that there will be no electron density on that plane, right? If you cut this molecular orbital like this, or if you cut this molecular orbital like this, right? Okay, if I'm cutting this molecular orbital like this, on this plane, right? On this plane, which is cutting the molecular orbital like this, right? On this plane, when it cuts the molecular orbital, there will be electron density on this plane. So there won't be any plane as such, right? There won't be any plane as such on which electron density will be 0. So there will be no nodal plane in this sigma 1s. Yeah? I'm sure it's clear to everyone, right? So let's take few more cases. Have a look exactly. Let's assume this is 2pz atomic orbital of one atom. This is 2pz atomic orbital of one more atom. First of all, have a look. Two same signs are on same side. So which kind of interference they are going to show? Constructive interference. And whenever there is constructive interference, which molecular orbital gets formed? Bonding molecular orbital gets formed. And in the bonding molecular orbital, the electron density in between the nuclei will be more, right? Due to which repulsions will be less and stability will be more, right? Let's say this is the nucleus of this atomic orbital, this is the nucleus of this atomic orbital. Now, how come electron density is going to be more between these two nuclei? Electron density will increase between these two nuclei only if the electron density in this lobe will try to enter into this lobe, and electron density in this lobe will try to enter in this lobe, right? Due to which this lobe is going to shrink, and this lobe, its width is going to increase. Even this lobe is going to shrink, and this lobe is going to get increased, right? So the final structure of the molecular orbital which gets formed over here in this case is going to be like this. right? This is, for example, negative, this is negative, and in the middle you have got positive, right? This is the nucleus over here, this is the nucleus over here, and this is the majority chunk of electron density which lies between the nucleus, right? Okay, so this is constitutive interference, and first of all, is it the axial overlapping? Absolutely, and axial overlapping always leads to the formation of sigma bond, so it's going to be sigma 2pz. I'll be calling this molecular orbital as sigma 2pz molecular orbital, right? As simple as that. This is what I call a sigma 2pz molecular orbital. So if I ask you, is there any nodal plane, right? There you won't be finding any single nodal plane in this one as well. You cannot cut this orbital in such a way that there'll be no electron density on that plane, right? If I cut it like this, there will be electron density on the plane cutting this molecular orbital. If you cut it like this, electron density will lie on this plane which is cutting this molecular orbital like this, right? You won't find a single plane on which electron density will be 0 in this molecular orbital, right? So again, there is no nodal plane. Yes? Correct? So 0 nodal planes. Now, let's take one more case. I'm sure everything is clear till here. Let's take one more case, guys. See, this is 2py, this is 2py, correct? Their axes are parallel. Now see, two same signs are on same side, so they are going to show the constructive interference again. It will lead to the formation of what? Bonding molecular orbital, because constructive interference always leads to the formation of bonding molecular orbital, right? And in case of bonding molecular orbital, electron density between the nuclei will be moved, right? By how much amount? 2 times psi A, psi B amount, right? So first of all, how this bonding molecular orbital is going to look like? See guys, first of all, as we know, these lobes will bend towards each other. Right? Okay, these lobes are going to bend towards each other. So they are going to be like this. Have a look. Have a look exactly what is going to happen. Right? See guys, these lobes have bent and these lobes have, the electron density has come between, right? The majority chunk of electron density has come in between. This is positive, so this part is going to be positive, this part is going to be negative. This was the nuclei over here, this was the nucleus of one atom over here. So, first of all, which kind of molecular orbital got formed? Bonding molecular orbital. By axial or parallel? By parallel overlapping. Parallel overlapping leads to the formation of pi bonds, right? So I should be calling this bonding molecular orbital as pi 2py molecular orbital, correct? People do it. Are you seeing any sort of nodal plane? Are you seeing any sort of plane which cuts this orbital, which cuts this molecular orbital in such a way that no electron density lies on it? If I cut it like this, there won't be any electron density in this plane. So I'll say there is one nodal plane which exists over here. So nodal plane is 1. Correct? Yes, I'm sure it's clear to everyone. So I'll be calling this as pi 2py. Similarly, let's take other examples as well. See, this is the same case which I've shown you, right? This is the nodal plane. Just above it, you'll find electron density. Below it, you'll find electron density, right? And there is one nodal plane in the middle. Yeah? Now, similarly, let's say this is dxy. Now, first thing, have a look. Same signs on same side. Right? So, which kind of interference? Constructive interference leads to the formation of bonding molecular orbital. So, again, they are going to show the they are going to form the bonding molecular orbitals, right? Now, what happens over here? Electron density between the nuclei should increase, right? Okay, so what should happen? See, this is the nucleus over here, this is the nucleus over here. So I'll say, in order to increase the electron density between the nuclei, I'll say this lobe, the electron density of this lobe, it should shift in this way. Electron density of this lobe, it should shift in this way. Similarly, electron density of this lobe, it should shift in this way, and electron density of this lobe, it should shift in this way, correct? Due to which, this lobe, they shrinks, this lobe and this lobe, they will shrink, right? Correct? I hope you're getting this properly. So, how it's going to look like? Have a look exactly how it's going to look. This is how it looks like. There is a nodal plane in the middle, right? This is the nodal plane over here. First of all, is it the axial overlapping or parallel overlapping? As you can see, this is the parallel overlapping. Parallel overlapping always leads to the formation of pi bond. So I'll be calling this molecular orbital as, this bonding molecular orbital as pi, for example, dxy, right? Okay, pi dxy. Yes? Right, Buell? Right now I'm only showing you the constructor interference. I'm not showing you the destructor interference, right? I'm sure everything is clear till here, correct? Right, people? So as you can see over here, this is how it looks like, right? So let me show it like this. Okay, this is how it looks like, your pi dxy. Let me move on to a few more. Okay, let me move on to something called as destructor interference. So till now you got to know by constructor interference what happens. Bonding molecular orbitals gets formed in which electron density increases between the nuclei, due to which the repulsions between the nucleus gets decreased, right? Stability gets increased. Now, what happens due to destructor interference? What happens due to destructive interference? Due to destructive interference, what is going to happen? Have a look, guys, exactly what is going to happen. See, let's say this atomic orbital of one bonding atom, atomic orbital of one bonding atom. They are going to show the destructive interference, right? Have a look. Have a look exactly what is going to happen. Let's say this is the wave corresponding to this atomic orbital, positive, negative. This is the wave corresponding to this atomic orbital, negative, positive, for example, correct? Are these waves in phase or out of phase? This is positive, this is negative. Are these in phase or out of phase? These are out of phase, right? They're going to show what? Destructive interference. So amplitude of resulting wave, what it's going to be? What is going to be the amplitude of resulting wave? It's going to be psi A minus psi B, correct? The amplitude of this atomic orbital, this wave was psi A, amplitude of this wave was psi B. So amplitude of this wave is going to be simply psi A minus psi B. If I do the square of this psi A, square of this psi A gives me the probability of finding the electron around the nucleus in A. Similarly, psi B square, it gives me the probability of finding the electrons around the nucleus in B, right? So what was I expecting? I was expecting, since the waves are combining, so the probability of finding the electron over here should be psi A square plus psi B square, right? This is something which I was expecting, which is not happening basically. This is the amplitude of A, psi A minus psi B, right? If I do the square of this amplitude, I'll be getting the electron density. So electron density is going to be psi A square plus psi B square minus 2 times psi A psi B. So is the electron density being increased or decreased? Electron density is increasing. I was expecting this much as the electron density, right, in the molecular orbital. But is the electron density increasing or decreasing? It's decreasing by this much of amount, right? The electron density between the nuclei is decreasing. If the electron density between the nuclei is decreasing, I'll say repulsions will increase. If repulsions are increasing, energy of the molecular orbital will increase, right? And stability will decrease. And due to this destructive interference, anti-bonding molecular orbital is formed. So this is the wave which corresponds to the anti-bonding molecular orbital, whose energy will be more, stability will be less. As simple as that, right? Let me show it to you over here properly. Let me show it to you over here properly. This is something which I've shown you already, correct? So when two waves combine in opposite phase, they lead to the formation, they lead to destructive interference, right? And due to destructive interference, electron density around the nuclei in the molecular orbital, that decreases, right? By how much amount? By 2 times psi A psi B amount, correct? Now, which kind of molecular orbital gets formed by the destructive interference? It's going to be anti-bonding molecular orbital, whose energy is less. Sorry, energy is more, stability is less, right? Okay, let me show you the case over here. See, guys, this is 1s atomic orbital, 1s atomic orbital, right? Positive, negative, positive, negative, positive, negative, right? So they are going to show what? They are going to show the destructive interference, right? Because two different signs, opposite signs are on same side, opposite signs are on same side, so destructive interference. And in the destructive interference, the electron density between the nuclei will decrease. And how it will decrease? This part of electron density will move in this way, and this part of electron density will move in this way in the resulting molecular orbital. So it's going to be like this, right? This was the positive part, this was the negative part, this was the negative part, this was the positive part, right? As you saw, this is the resulting molecular orbital which got formed by the destructive interference, and due to destructive interference, which molecular orbital gets formed? It is going to be the anti-bonding molecular orbital, in which the electron density between the nuclei has decreased, right? So is it the axial overlapping or parallel overlapping? This is the axial overlapping, and axial overlapping leads to the formation of sigma bonds, right? So this is going to be sigma 1s or sigma star 1s. It's going to be sigma star 1s, right? So is there any nodal plane over here? Yes, absolutely. There is one nodal plane which lies over here, right? You can cut this orbital in this way, and on the plane which is cutting the orbital, there won't be any electron density. So one nodal plane in this one, yeah? I'm sure it's clear to everyone, right? So this was sigma star 1s, correct? Let me take a few more examples. This is 2px, this is 2px, right? They are going to show the restricted interest, positive, negative, right? Opposite signs on same side, right? Restricted interference leads to the formation of anti-bonding molecular orbital, right? And in case of anti-bonding molecular orbital, electron density in between the nuclei will decrease. So how electron density in between the nuclei will decrease? When this lobe, the electron density in this lobe will shift in this way, and the electron density in this lobe will shift in this way. What is going to happen due to that? Due to that, you are getting something like this. You got something like this. Have a look. This lobe, it shrinked, as you can see. This lobe, even it shrinked, as you can see, right? This lobe, its width increased. Similarly, the volume of this lobe, it also increased, as you saw. Basically, volume of this lobe and this lobe basically are increasing because the electron density are moving towards them, right? So let me give the signs as well. This is negative over here. This was positive. This is positive. This was negative over here, and this is positive over here. Correct? Are you seeing any nodal plane over here? Yes, in the middle you are seeing one nodal plane. Correct? You are seeing one nodal plane. And if I ask you, is this axial overlapping or parallel overlapping? This is axial, head-on overlapping. Head-on overlapping leads to the formation of sigma bond. So the molecular orbital which I got over here, this is first of all anti-bonding molecular orbital. And how do I represent it? It's going to be sigma star 2px. This is sigma star 2px, right? I'm sure it's clear to everyone. Yeah? Right? Let's take a few more cases so that it is clear to you. As you can see over here, there is one nodal plane, and we represent this by sigma star 2px. Yeah? Perfect. Okay, there is one more case which I'm going to show you now. See. Positive, negative. So, destructive interference. Which molecular orbital? Anti-bonding molecular orbital. Electron density will decrease in the molecular orbital, right? In the molecular orbital, electron density is going to get decreased. By how much amount? 2 times psi b. And how electron density in the molecular orbital will decrease? It's simple. Where this molecular orbital, this lobe of atomic orbital will shift in this way. This lobe of atomic orbital will shift in this way. This lobe of atomic orbital will shift in this way. This lobe will shift in this way, such that you get the resulting structure like this. Right? This was positive, this was negative, this was negative, this was positive. First of all, is this head-on overlapping or parallel overlapping? It's parallel overlapping, right? And parallel overlapping leads to the formation of pi bond, right? So I'll be calling this molecular orbital as pi, but this is destructive interference, so pi star, it's going to be 2py. If I ask you, is there any nodal plane? You can cut this molecular orbital like this as well as this, right? So on both the planes, there won't be any electron density, so we have got two nodal planes over here in case of pi star 2py, yeah? I'm sure it's clear to everyone, right people? Yes? Right? Let me take a few more cases. Okay. These are the two d orbitals which I've taken over here. These are the two d orbitals which I've taken over here, right? See, first of all, positive, negative, this is positive, correct? So, by just looking at the signs, you got to know over here destructive interference is going to happen, right? Because opposite signs on same side leads to destructive interference, and due to destructive interference, which kind of molecular orbital gets formed? It's going to be anti-bonding molecular orbitals, right? And in the anti-bonding molecular orbitals, the probability of finding the electron gets decreased by how much amount? 2 times psi b, right? So what happens? How electron density between the nuclei is going to get decreased? When this lobe, electron density in this lobe will shift in this way. Electron density in this lobe will shift in this one. Similarly, some part of electron density in this lobe, electron density in this lobe will shift in this way, and electron density in this lobe will shift in this way, right? If the electron density in this lobe is shifting towards this way, right? So I'll say this lobe is going to get shrinked. Even this lobe is going to get shrinked. This lobe is going to get shrinked. This lobe is going to get shrinked, right? So how you are going to represent it? The final molecular orbital you are going to represent like this. Final molecular orbital you are going to represent like this. Right? Let's put the signs. Let's give the signs. Have a look. This was positive, and this lobe which got shrinked is negative. So this was positive. This lobe which shrinked is negative. This was negative. This was positive. So this is negative. This one is positive. Similarly, this lobe which shrinked was negative. Right? This lobe which shrinked was negative, so this is negative, this is positive, and over here, this is going to be negative, this is positive, correct? Right? So first of all, if I ask you, Is this a destructive interference? Yes. Is it going to form the bonding molecular orbital or anti-bonding? It's absolutely going to be anti-bonding molecular orbital, right? So was it axial overlapping or parallel overlapping? It was the parallel overlapping, right? So pi bond. So is it going to be pi or pi star? It's going to be pi star. What? Pi star D. Let's call this as D, 3dxy. Let's call this as 3dxy as well. Okay? So it's going to be pi star 3dxy. Right? So if I ask you how many nodal planes are there, this is one nodal plane cutting this orbital in this way, one more nodal plane cutting this orbital in this way. So there are two nodal planes in this pi star 3D xy. Yeah? I'm sure it's clear to everyone. Right, people? So there are two nodal planes as you can see over there. Yeah? Okay, so I hope you got to know exactly how these molecular orbitals get formed, right? Constructive interference always leads to the formation of what? Constructive interference always leads to the formation of your bonding molecular orbitals, and destructive interference always leads to the formation of what? Anti-bonding molecular orbitals, correct? Yes. Let me just give you the quick overview of few things which I told you till now, right? So that you can remember them properly. I told you atomic orbitals of two bonding atoms, they are going to combine. They will lead to the formation of two molecular orbitals. One is going to be bonding molecular orbital, one is going to be anti-bonding molecular orbital. Bonding molecular orbital is formed by the constructive interference. Anti-bonding molecular orbital is will be getting formed by the destructive interference. Due to the constructive interference, the electron density in the bonding molecular orbital will increase by how much of amount? The electron density increases by 2 times psi A psi B amount, right? And in case of anti-bonding molecular orbital, the electron density decreases by how much amount? 2 times psi A psi B, right? Electron density decreases by this much amount. The electron density is increasing in bonding molecular orbital between the nuclei. There will be less repulsions. Less repulsions means less energy, and less energy means more stability, right? Similarly over here, electron density between the nuclei is decreasing. If it is decreasing, repulsions between the nuclei will increase. Energy of the anti-bonding molecular orbital will increase, and eventually stability will decrease, right? In case of constructive interference, two waves are in same phase. They'll be in same phase, right? In case of destructive interference, two waves are in opposite phase, right? They're going to be in opposite phase, correct? This is something which you have discussed till now, right? Okay, and people, by constructive interference, molecular orbitals get formed. By destructive interference, anti-bonding molecular orbitals get formed. So till now, we exactly saw how these bonding molecular orbitals and anti-bonding molecular orbitals gets formed. Now, in the tomorrow session, I'm going to continue from here, right? Since till now, we saw how these molecular orbitals get formed. Now, after this, I'm going to show you how electrons are distributed in these molecular orbitals. After the distribution of electrons, we'll see exactly how to find the bond orders, right, of every species, how to compare the bond lengths, right? Every single thing will be done in the tomorrow session, right? And tomorrow only, we'll be doing the previous year questions as well from the chapter chemical bonding. So do attend the tomorrow session, in which I'll be discussing about the bond parameters, in which bond order comes, bond length comes, bond energy comes, and at the same time, we'll be discussing some previous equations, around 20 to 30 previous equations from this chapter of chemical bonding, right? So I'm sure you would have enjoyed the session and you would have made proper notes till now. I'm sure about that. And before ending the session, people, so the ones who have not enrolled in the long-term batch yet, people, this is basically the EdFest going on currently in Vedantu, in which you are getting 50% off on all the courses, right? And in order to avail this offer, you just have 2 more days, right? In order to avail this offer, you just have 2 more days. So in order to be with us for complete 2 years, if you want to get trained by us in all the 3 subjects with us by the teachers of your choice in your physics, chemistry, biology, right? Or physics, chemistry, maths, right? You need to take any of the pro subscriptions, right? And currently 50% off is going on due to the Shira, right? So people, we have got 3 pro subscription for you. You can enroll in light, or you can enroll in classic, or you can enroll in plus, right? So people, these are all the pro subscriptions which are valid for the ones who are going to write NEET in 2023, right? So basically for complete 2 years, you are going to be with us on our actual Vedantu platform, apart from these YouTube sessions, right? Okay, and this is the course fee for light program, this is the course fee, complete course fee for 2 years for classic, and this is the course fee for plus, right? And if you're new to Vedantu, you have no idea how the actual Vedantu platform looks like, right? No need to pay this much of amount in one go, you can pay this much amount in installments as well. And at the same time, if you want to try these Vedantu classes, actual Vedantu classes on actual Vedantu platform, right, you can take the subscription for a month, and for a month, no need to pay this much of amount as well. There's a 50% off going on, correct? Use the code WSPRO, you'll be getting 50% off, right? Just reduce the price again, you'll be getting enrolled in the batch, in the actual Vedantu platform batch, right? In which we train the kids for the NEET 2023, right? So do take the class for a month through this pro subscription or through this, right? The choice is all yours. And trust me, you're going to love it. When you enter into actual Vedantu platform, you're going to love it, right? The classes are actually far, far better than the YouTube classes. Trust me on that. Anyways, so this is the EdTech Fest. And due to this, you are getting 50% off on all the courses which I've shown you over here. So let me show you exactly how to get enrolled in the batch. Before that, the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel. And at the same time, let me show you exactly how to get enrolled in the Vedantu platform. This is the video which you guys are currently watching. You need to drag it a little down, click on this show more. After clicking on this show more, you'll be getting a lot of links. So majority of the people currently are looking for CBSE term 1 crash course. If you are also looking for the CBSE term 1 crash course, right, click on this link. After clicking on this link, you'll be having two plans. The choice is all yours. You are just getting this crash course for 1500 by applying the coupon code, right, because 50% off currently is going on. Okay, this was for the ones who are looking for the CBSE term 1 crash course. If you are looking for the NEET 2 years, right, click on this link and be with us for 2 years. You can take any of these plans, right? Okay, if you are taking this plan, for example, for a month, you just need to pay 1500, that's it, because 50% off is going on currently. And at the same time, you can take any of these plans. The choice is all yours, either classic or plus or whatever. In plus, you get the personal mentor in all 3 subjects, right? And people, at the same time, if you are looking for the NEET droppers batch on the actual Vedantu platform, click on this. After clicking on this, you'll be getting again 3 links, and you can take any one of these plans, right? You can try them out for a month as well, correct? By using the coupon code WSPRO, by clicking on try for a month, give your number, give your email, and eventually you get enrolled in the long-term batch, right? Well, this was all for today. So people, I'm going to take one more session at 10:30 sharp on Vedantu JEE English channel, in which I'll be discussing some important questions from the chapter Chemical Equilibrium, right, for class 11 students only. Sharp at 10:30 tonight. Join me on Vedantu JEE English channel. It's going to be fun. Trust me on that. So let's meet up again at 10:30 on Vedantu JEE English channel. Hari Kishore, which chapter we are going to do next? So next chapter is going to be General Organic Chemistry, right? Okay, so do let me know if you want the General Organic Chemistry, the next chapter after this chemical bonding. So let's take a leave. See you at 10:30 tonight sharp on Vedantu JEE English channel. Till then, you take care, guys. Take care. Bye-bye.